In the previous lessons, we saw that, when discussing the railway sector, it is essential to consider an energy binomial composed of both trains and the supporting infrastructure, such as stations, depots, and signaling systems. While trains are extensively studied and are generally quite energy efficient, stations and other non-traction infrastructure often receive less attention in energy efficiency discussions. However, non-traction infrastructure accounts for around 10% of the total energy consumption within the railway sector, a share that cannot be ignored. Improving the energy efficiency of these buildings and systems can contribute significantly to reducing the overall energy footprint of railway transport. Given this context, this lesson will focus on train station networks, introducing an innovative approach to measuring their energy usage and identifying strategies to enhance their sustainability. The adoption of traditional approaches to improving the energy performance of buildings, such as analyzing individual stations using dynamic simulation tools, can certainly be effective for a single station. However, these methods fall short when it comes to providing a comprehensive overview of the entire railway system energy efficiency. One promising way to address this limitation is the adoption of a bottom-up modeling approach that can offer insights on a broader scale, enabling informed decision-making for strategic improvements across the entire station network. This approach involves several key steps. The first step is gathering detailed information about the railway stations within the network under study. Based on this data, stations are categorized and several archetypes are defined by clustering those with similar attributes. Next, detailed physics-based dynamic simulation models are created using building energy modeling tools. These models serve as the foundation for constructing a surrogate mathematical model, which provides stakeholders with an easy-to-use tool for analysis. This simplified model enables stakeholders to explore various retrofit scenarios and energy-saving measures effectively. What sets this approach apart is its ability to account for multiple factors, such as building geometry, construction material, SVSC systems, and operational patterns, while still keeping the focus on a broader scale. In this way, the simulations offer a detailed calculation of energy consumption, making it easier to pinpoint specific areas for energy efficiency improvements. To demonstrate the effectiveness of this methodology, it is applied to a case study involving the Italian railway building stock. The network features a different range of building types and sites, each with its own unique energy consumption profile. Using the described methodology, it is possible to classify this network by clustering buildings with similar characteristics. Specifically, referring to the taxonomy presented in the dedicated lesson, 4 station building archetypes can be identified, based on their size and significance within the system. Bronze stations, silver stations, gold stations, and platinum stations. Bronze stations are small stations or stops, equipped primarily for regional or local traffic, typically serving an average of 500 daily users. Silver station group includes medium to small stations that provide urban, suburban, or metropolitan services. They usually handle an average of 2,500 daily users, with some accommodating up to 4,000. Gold stations are medium to large in size, offering high-quality services for long, medium, and short distance travelers. They also provide amenities for non-traveling visitors and handle an average of 10,000 daily users. Finally, platinum stations include large stations that serve long, medium, and short distance passengers, including those of high-speed trains. Like gold stations, they offer services for non-traveling visitors. Platinum stations typically serve around 20,000 daily users. However, due to their diversity and complexity, platinum stations are excluded from this analysis as they require more specialized consideration. For the remaining bronze, silver, and gold stations, 3 building prototypes can be identified by sampling the geometries of existing railway stations. Using these prototypes, different archetypes are created by considering 5 climatic conditions corresponding to Italy's weather zones, 4 heating and cooling strategies, and 4 different electric load intensities. By combining these variables, 80 unique archetypes are generated from each building prototype. Then, For each archetype, dynamic simulations are conducted using a physics-based dynamic simulation tool. To simplify the analysis, a linear regression approach is then employed to create a reliable yet straightforward surrogate model, which can be used as an alternative to the detailed simulation model. The specific details of these steps are omitted here for the sake of brevity. Using the developed surrogate model, the entire Italian railway network can then be analyzed, with a specific focus on energy retrofit actions across more than 2,000 railway stations. 3 systematic energy retrofit strategies are evaluated for this specific case study: improving the energy performance of building envelope, renovating the heating, ventilation and air conditioning systems, and implementing more efficient lighting systems. The potential benefits of these strategies can be assessed by comparing day energy consumption to that of the baseline. In terms of results, reducing electrical loads by means of more efficient lighting systems emerges as the most impactful strategy, with a potential primary energy savings of approximately 26%. This is followed by efficiency improvements in SVSC systems, which offer savings of 14.3%, and envelope improvements contributing 1.2% in energy savings. It is important to note that the majority of the Italian railway station building stock consists of small to medium-sized passenger buildings, many of which are unconditioned. Therefore, the greater impact of electricity consumption compared to air conditioning is understandable. However, this may not hold true for certain stations, particularly the platinum ones, which require more customized analysis. It is important to note that these results are specific to the case study analyzed. Different outcomes could be achieved by investigating alternative energy efficiency actions or by studying different railway networks. Nonetheless, the findings demonstrate the effectiveness of the proposed method in generating valuable insights that support data-driven decision-making. By concluding, this lesson demonstrates that using advanced analytical tools and methodologies like the bottom-up modeling strategies for railway station analysis is essential for promoting sustainability of railway networks. By adopting such approaches, railway authorities can make data-driven decisions that not only improve energy efficiency but also contribute to broader environmental objectives, such as reducing greenhouse gas emissions.